Are there questions?
Yeah, actually.
Yes.
Here, like, moduli space is like 2 and minus 6 dimension.
Yes.
Then if you put n equal to 2, then you will have 2.
Yes.
Then that you take to be the position of the fourth operator.
Yes.
So then this is the moduli space. Moduli space is now this position of the
Fourth operator, yes.
Then what is the boundary? No boundary.
No, the boundary is when the fourth operator approaches the other three. Yes. So if we have 4 punctures, then there is a moduli space, right? This theory, this has this 6g minus 6 plus 2n. That's the formula, right? So for 3 punctures, there is no moduli space because of the conformal killing vectors. But for the 4th puncture, there is a moduli space, and the moduli space is the plane or the sphere minus those other 3 points, right? Those are the boundaries. Yes. So if you want to, last time I described the coordinates near the boundary, right? Okay. So let's see how to describe this, the coordinates on a boundary. So let's suppose that we have 2 spheres, one with 3 punctures, another with 3 punctures. These are the original punctures, 1, 2, 3, 4. And these are identified as W1, W1 prime equal to Q. Okay. So in this case, we can take W1, W. So let's take these at 0. Sorry, let's take these as 0, 1, and infinity. And similarly, we take 0, 1, and infinity. Right? For 3 puncture sphere, you can take the punctures to any value like. Exactly. So the only moduli is a Q. Yes.
So that is what moduli
Exactly. Okay. So Q will label the moduli space of this bigger thing. Okay. So let us see how Q relates to what we normally understand, right? That the positions of the punctures. Okay. So in this case, let's take W1 to be Z1 and W1 prime to be Z1 prime, where this is the coordinate on the first upper on plane, coordinate on the first plane. Sphere and plane are the same, right? So I think of this as a coordinate on the first plane and this Z1 prime as a coordinate on the second plane. Okay. So after you have identified this, there is only one object, right? Okay. And we can use either Z1 or Z1 prime to label that sphere. Okay. So let's choose Z1, right? So let's take Z1 to be the sphere, to be the coordinate on the final sphere. Okay. So you see that the puncture 1, this levels to puncture. Which puncture you are using? So Z1 was already a coordinate on this system. So the puncture 1 is at 1. Okay. So Z1 is 1. And puncture 2 is at infinity. Okay. Puncture 3, this coordinate was known in the Z prime coordinate, right? Okay. But we now have this identification. Okay. So this translates to Z1 prime equal to Q. Okay. So Z3 is Q over Z3 prime. Z3 prime was at 1. So this is Q. Yes. So Z3 is Q over Z3 prime is 1 and Z4 is Q over Z4 prime. But Z4 prime was infinity. So this is 0. Okay. So in the final sphere, Okay? The punctures are located at 1, infinity, q and 0. Okay? And now you say q goes to 0 means what? Q goes to 0 corresponds to Z3 and Z4 coming close.
And that looks like that 3 comes and hits.
Yes, if we use the Z1 prime coordinate system, right? Then it will look like Z1 and Z2 coming close. Right? In the Z1 prime coordinate, Z1 and Z2 will come close. In the Z1 coordinate system, Z3 and Z4 will come close. But they are conformally equivalent. Right? Because once things come close, right, you can always increase the distance by scaling. Okay? And what will that do is that the other 2 points are going towards infinity. Then we make a Z2 1 over Z. Right? So then those 2 points which are going to infinity will come close. Right? And these other 2 points will remain at finite distance. Is this clear? Right? So the other boundaries will come from other grouping, right? When, say, the first one will have the punctures 1 and 3, second one will have punctures 2 and 4. Yes, but this is local coordinate, right? Q going to 0. You also have other boundaries of this. No, not Q going to other points, right? The other boundary is where this side may have a punctures 1 and 3, and this side may have punctures 2 and 4. That's a different boundary, right? So there, if you take Q goes to 0, that will correspond to 2 and 4 coming together, or equivalently 1 and 3 coming together.
Yeah, Q. This coordinate just means 3 and 4 coming closer.
Yes, for this degeneration, right? But every possible degeneration is a boundary, right? So this corresponds to a degeneration of the sphere when it looks like this. On this side you have 1 and 2, on this side you have 3 and 4, right? But there are other degenerations which is like this. 1 and 3, 2 and 4. This is a separate boundary. Yeah, all possible necks you have to pinch, right? So every degeneration corresponds to pinching of some neck. So all possible necks you have to pinch. And in this case, the neck, this neck, right? If you think in terms of the original sphere, right? 1, 2, 3, 4. Then this neck pinching is what we described there. Right? This neck pinching is what we described here.
Some condition where 1 and 3 will come together.
When here, for the other pinching, yes. So you just do exactly the same thing, right? With 3 and 2 exchange, right?
That will be a different Q. That's what you're saying.
Yeah. So Q corresponds for every handle, right? Has a corresponding Q, right? And that Q going to 0 is the pinching of that hand. Right? So there's a different coordinate system. There are different boundaries. You have to erect different coordinate systems. Right? The original Q here will become something else.
We can relate this to this Q and that Q. Otherwise, it seems like.
Yeah, in this case we can. In this case we can. Right? But it's just like when you have a manifold, right? As you move around, right? In different regions, it's useful to use different coordinate system. Right? The point near the boundary, it is useful to use this Q coordinate. No. Q goes to infinity is fine. See, Q will keep, as I said, the way we have parameterized, right? Is the Q goes to 0 limit is the boundary. Right? Q goes to infinity doesn't have a universal description. So if Z3 goes to Z2, you will introduce a different coordinate system there.
Q goes to 1 also, it looks like Z1 like 1 and 3 are coming close.
Q goes to 1, no, Q goes to 1 in this case, 1 and 3 probably don't, yeah, Q goes to 1 in this case, 1 and 3 come close, right? But that's an accident. We could have taken the local coordinate, right? Instead of using this, right? We could have used W1 equal to some Z1 over lambda or lambda z1 for some arbitrary constant lambda. Then everything will scale, right? Then the q goes to 1 is the regular point. So typically one chooses the local coordinates so that for mod w1 equal to 1, right, it describes a small region in the z plane, right? So that you are really, that even for q equal to 1, that means that you are gluing two small circles, okay, because you are really wanting to parameterize the coordinate near the boundary.
It seems like, pinching is always like two coordinates, two insertion points coming together.
On the sphere, yes, that is true.
On a sphere.
Yes.
So can I do something like this where degeneration is happening and in this sort of bubble, there is just one insertion or no insertion?
Degeneration, no, you cannot. No.
Because it's sphere with one and
Yeah, sphere with 1 and 2 doesn't make sense. Yeah, exactly. Right. So sphere with 4 punctures have a degeneration where it splits into 2 spheres, each with 3 punctures. Right? You cannot have a degeneration where on one side you have a sphere with 2 punctures or 1 puncture.
But is there some threshold genus value where sort of partition function or amplitude is defined with no insertions?
Yeah, genus 2 onwards, yes, you can define it.
There, but okay, so probably the statement there is that the moduli space has no boundary.
No, that also you can pinch, right?
I can pinch, but
A genus 2 surface,
yeah,
like this, right? You can pinch this cycle.
but
Torus with 1 puncture.
But
It will become torus with 1 puncture.
torus is
Exactly. 2 tori each with 1 puncture. So that's perfectly good.
okay, so there is the boundary.
Yeah.
It seems punctures and like double points because in this case you have two spheres at the boundary that are attached together with one.
Yeah, but when you think in terms of this picture, right? Here you really have 2 independent spheres which are being glued together, right? So when I say it has 3 punctures, it's in this sense that there is a puncture here. That when you think of this as showing 2 spheres, right? This puncture will belong to both spheres, right? As this Riemann surface, there is a double point, right? When you pinch it. But from the point of view of the description where you think of this as a gluing of 2 Riemann surfaces, there you really have 1 puncture on each side. Yeah, that's the most useful description near the boundary.
The situation where 3 of the points are coming together and 1 point is going away.
That type of situation doesn't exist here.
Because, right?
Because how can you break 3 points are fixed? Right? You cannot have that kind of thing here. So on the sphere, there is no boundary, but 3 points come together and 1 point is away. If you have a sphere with 5 punctures, it can happen. Right? There are 3 points coming together is conformally equivalent to 2 points coming together. Because 5 punctures, 3 points coming together means what? You are pinching a neck, right? On one side there are 2 punctures, one side there are 3 punctures. That is certainly possible.
One coming close to Z2 is equivalent to Z3 coming close to Z4.
Yes, that is true. Yeah.
We have to count different. First you do this and then you do the other one. Z1 and Z3 coming. That is
Exactly. Yeah. Yeah. And then Z1 and Z4 coming close. Right? So those are the inequivalent degenerations. Those you have to count separately.
Here is slightly special because we have this global coordinate Z. We didn't have Z1.
That's okay. I mean, on the higher genus surface, what it matters is the surface nearby, right? The coordinate system nearby. You have a W that encloses the disk, right? And then there is a region outside, right, which you have to call Z. Right? You can use that coordinate to measure the location of the puncture. See, intrinsically, you can think of this as some abstract parameterization of the moduli of the surface with 1 puncture. Right? It doesn't matter how you parameterize, right? Because so far what you have said doesn't depend on that parameterization. That here it just so happened that the parameter, you don't have to parameterize because these have no moduli anyway. Right? But we have to choose a local coordinate system. Right? So this q, so for example, the 0 less than q less than 1, right? We will restrict q to that range. How much of the moduli space it covers, that depends on what local coordinate system you have chosen. Right? If you take, as I said, this lambda, right, will mean what? I mean, there will be extra lambda somewhere, right? So if you define it this way, then z1 prime will be q over lambda square, right? Yeah, so z1 prime will be q over lambda square. Yeah, so z3 will be q over lambda square. Okay, and for large enough lambda, you can see that as q goes between 0 and 1, that you are not coming close to any other point. Because, okay, 0 less than q less than 1 covers only the region near one boundary. This is what we'll assume, that we have chosen our local coordinates in such a way that between q equal to 0 and 1, the only boundary that is there is the q equal to 0 boundary. Right? So that this other issue that for q equal to 1, z1 goes to z3, that problem will not be there.
Two boundaries can also have an intersection.
Yeah, but it's always possible.
At the intersection.
No, at the intersection is fine. Then there are, I mean, at the intersection means what? So there are two parameters, q1 and q2, right? And q1 going to 0, q2 going to 0, both can go to 0. That is certainly possible.
Yeah, and both going to 0 is a different kind of degeneration.
Exactly. Yeah.
Yeah, so
problem I guess is that q1 going to 1 or something gives me another.
q1 goes to, yeah, so you don't want that. Yeah, you don't want q1 going to 1 to give you another boundary.
This lambda.
Exactly.
Lambda large.
Yeah, if you take lambda to be large, right, then you can see that the boundary part of the region that is covered is close to the boundary. No, we want q goes to 0 to correspond to one kind of degeneration. Right? There can be degeneration within degeneration. Right? That if we take, for example, the 5-point function, okay, you can pinch this first, right? Pinch this cycle. That has an associated q1. But on this side, now we have 4 punctured sphere. Right? So now you can again pinch this side, this one. Right? So there are different parameters. This is q1, that is q2. No, independently they are integrated from 0 to 1.
This kind of degeneration will not happen. Doing this, we have 3 punctures only on one side.
But 4 punctures on the other side. That 4 puncture sphere can degenerate.
Yeah. Not the first case.
No, first case, no, nothing. First case, they are, yeah, exactly. Q is the only parameter and that's the degeneration. But when there are more than one parameters, right, you can have degenerations like this.
This case was also 4 dimensions.
Exactly. That's right. So you have Q1 and Q2. Okay. And in string field theory, in fact, it's much simpler to see this because each of these degenerations correspond to a Feynman diagram. Right? That this pinching a neck basically, like here, for example, right? This region from 0 q equal to 0 to 1. Okay, if you take the q equal to 0 to 1, that covers some region of the moduli space, right? In the 4 punctured sphere. That you interpret as a Feynman diagram where 1 and 2 goes to 3 and 4. Okay, the leg that pinches is the internal propagator. Right? That's how you think in the language of string field theory. Similarly, this one will correspond to 1, 3, 2, 4. Right? So ST and U channel diagram. So there is another diagram which is like this: 1, 1 to 4, 2 to 3. So each of these will correspond to some region of the moduli space. And then whatever is left, you interpret this as the contact term. Okay, so basically the way the string field theory organizes the terms as sum over Feynman diagrams is that it takes the whole moduli space and cuts up into pieces. Okay. The piece that has no propagator, okay, that is the bulk, that has no degeneration. Okay. Piece with one propagator corresponds to having one parameter which is becoming small and that one boundary. Okay. If there are two propagators, that includes a region where there are two boundaries are intersecting, right? Q1 equal to 0 and Q2 equal to 0. Right? That's like two boundaries, two different boundaries intersecting and so on. So you can make a one-to-one correspondence in the Feynman diagrams, and this way of decomposing the moduli space. Okay, later we will see even closer connection to these Feynman diagrams. That is our choice. We just choose Q to run from 0 to 1.
It's like lambda is controlling.
Yeah, so lambda is basically controlling how much region it covers. Pardon? Lambda is arbitrary. You can choose to be whatever you like. It's useful to take lambda to be large. See, otherwise what may happen is that some region of the moduli space may get covered twice, right? From one Feynman diagram and another Feynman diagram. Which is not a problem because then that will mean that in the definition of the 4-point vertex, you have to subtract from that region. Right? Instead of saying that the 4-point vertex covers the rest of the region, you have to subtract that off. So it's just somewhat inconvenient to do that. So you just use the large lambda kind of coordinate system, okay, so that the Feynman diagrams cover a part of the moduli space. Right? The Feynman diagrams with propagators, and then whatever is not covered, you declare as a new vortex, interaction vortex of the theory.
Is this lambda ambiguity related to redefinition?
Yeah, so this lambda ambiguity, if one can show, is related to some field redefinition in string field theory. Right? This is the kind of thing that Aninda was describing yesterday. That
Same lambda.
yes, same lambda. Yeah. Right. But of course, I mean, there are more than one lambda, right? I mean, you can use this choice of local, this W, right, is a whole function, right? I have said W equal to Z, proportional to Z, right? But there's no need to do that. W could be lambda Z plus lambda prime Z square, right? So this choice of W there is an infinite dimension ambiguity, and that's related to the fact that field redefinition also has infinite ambiguity. Is this clear?
One question, 2-point, like if you wanted to write a 2-point diagram, minimum need a genus of 1.
2-point diagram.
For a non-vanishing 2-point diagram.
Yeah, unit genus 1. Yes.
Properly sort of vanishing.
No, not that the propagator is vanishing at the tree. On-scale propagator does vanish at the tree level, right? Because it's k square. Right? So that's the statement. If you take the Lagrangian, right, it's phi box plus m square k phi, right? In the moment of it's k square plus m square, and k square plus m square is 0 on-scale. Right? So it's basically a reflection of that fact.
The degeneracy of this separating type.
Degenerations of separating type, but the same kind of thing will work for non-separating type. On the sphere, there is also non-separating type. On sphere, all degenerations are separating type. Right? But on the torus, you can pinch and handle. Yeah, you will get a torus again. So you will get a sphere, right, with more punctures, 2 more punctures. Well, that's loop. Yeah, like this, right? So this is a torus 2-point function. Right? There is a contribution to torus 2-point function, right, which corresponds to taking the 4-point interaction on the sphere and connecting this by a propagator. This line is getting pinched. The degeneration is that on the torus, we have 2 points, right? And this is getting pinched. Okay? So when this is getting pinched, right, how will you describe this? Right? You cut it open, right? So then it becomes a sphere with these 2 points are there and then 2 more points, right, which are the points on this sphere when you have pinched it. Okay? And then we erect again local coordinate W1 prime on this and write W1 prime equal to Q. That, and then you will take Q between 0 and 1, mod Q between 0 and 1.
Yeah, almost like here you wanted to identify different boundaries of the moduli space and contributions from different finite.
Same here, the Q goes to 0 limit of this, right, or the region between Q equal to 0 and 1 is this particular Feynman diagram.
That's the usual one. That's not the boundary of the one.
No, in front of Feynman diagram is always the usual one. This is also the usual one, no? This one represents a contribution that includes boundary of the moduli space.
Just the boundary.
Just the boundary, there is no, it's a region around the boundary. Just the boundary doesn't make sense, right?
Region around boundary.
Exactly.
And the rest of the region you identify with the contact diagram.
Exactly.
So in the torus 2-point
Okay.
moduli space, if you try to do this segregation, something near the boundary and something there.
Exactly.
What are the 2 Feynman diagrams?
Well, there are 3 Feynman diagrams in this case. Right? There is one here, right? Then there is one here. Okay, this is double degeneration.
Oh, after the you make the sphere again.
Yeah, right. So this is double. So this sphere 3-point function, loop to a torus 1-point function, but the torus itself is degenerating. Right? And then there is a contact term, 2-point contact term.
What is the subdiagram?
A phi square term added to the Lagrangian. Well, may not have, it may vanish for a k square equal to 0, depending on what form it takes. Right? It may change mass also. The total change in mass is not just this, right? Yeah, this is also mass transformation diagram. So everything has to be added. Is clear? So if you are trying to classify the degeneration, say in genus G, right? What are the all possible degenerations? In a genus G endpoint function. Right? What are all possible degenerations? You take a genus G, a G loop endpoint Feynman diagram, G loop endpoint amplitude, right? And draw all possible Feynman diagrams. Okay, those will be the degenerations. So every Feynman diagram is like pinching a cycle. Every propagator is like pinching a cycle. One loop has these 3 diagrams. This, and this. 4 diagram. There is one more. So no, maybe there is one more. Yeah. This one. Yeah. Right? And this one. Yeah. Yeah, everything that you can think of to draw. Which one? This one? Oh, this one is the same as that. Yeah, we have drawn it. Okay. Okay, fine. Yeah, but this one is there. Okay. This one means what? Like, let's look at this. This one means that you have a sphere with 3-point function, because these are the vortices, right? Okay. Then you identify this one with this one, right? By this W1, W2 equal to Q, right? And then you further identify this one with this one. So there are 2 Q parameters, right? One from here, one from here. Q1 running between 0 and 1 and Q2 running between 0 and 1. That is this Feynman diagram. That is also double degeneration, yes. Number of degenerations is the number of propagators. Internal propagators. This one has two internal propagators, right? So it's a double degeneration.
What is without these, the straight line?
That's this is a without degeneration. Contact term. Right? Every time you have an internal propagator, that means you have some q that you are integrating from 0 to 1. So that q going to 0 is a degeneration. It's okay?
This in this there also, but in the sphere case, the contact diagram is some lambda 4, 5, 4 kind of.
Yes.
And this is some lambda 3 square kind of.
Yes.
I mean, lambda 3, 5, 2, but the
Yeah.
contribution is a lambda 3 square.
Yes.
So you are also saying that lambda 3 square is like lambda.
Yes, the J's counting goes like that.
That is
built in the
built in.
yeah.
Even there.
Yeah. Because GS to the 6G minus 2G minus 2 plus n, that formula is there, exactly. Right? So that is already built in. This one? Okay, now you can see what it will be on the sphere. So there are 3-point function, sphere 3-point function, right? That's this one. Then that is being glued with another sphere 3-point function. Right? So identify these two. Right? And then we have another two. So you identify these two. Yeah, so that's this diagram. So once you read a Feynman diagram, it's easy to figure out what degeneration corresponds. Right? What kind of swaying there is. Because Feynman diagram, the Feynman propagators are the swaying operators. Right? And we will see it in the equations later. Why are these like Feynman diagrams? Well, you can do it only in a very special case, that is the Witten's cubic string field theory. Otherwise, no. Otherwise, typically you have to have contact diagrams. Witten's cubic string field theory is the only known theory, right, where you don't have contact diagram. That corresponds to a very particular choice of lambda. Right? And also, these W's are complicated functions of Z. It's not a SL2R in that case. The relation between the local coordinates and the global coordinate on the sphere, right, is not an SL2R relation. It's a more complicated relation. But with that, you can ensure that there are no contact diagrams. Even at all genus, all loops, all loops, you don't get any contact term.
Modularized space is like wide. How can you ensure that there is no gap?
But yeah, that's exactly how you prove that there's no gap left. Right? With that particular choice, right, you basically show that there's no gap left.
Any other string field theory is a redefinition?
Open string field theory. But normally we would want closed string field theory. Yeah, we are doing closed. For closed string field theory, there's nothing. There is no formulation where the contact terms are absent. Yeah, exactly.
Just put some boundaries.
Yeah.
That reduces the modulus space. What is it?
Yeah, it makes it half basically, because like for a disk n-point function, right, the number of moduli is n minus 3 real variables, right, instead of 2n minus 6 real variables. Okay, let us go back and try to get some equations from here, right, this procedure. So let's suppose that we have two Riemann surface with lots of punctures, and then you have one which we are going to use for swaying. So here we have chosen a local coordinate W1. Here you have chosen a W1 prime. Okay. And we have used the showing relation W1 prime equal to Q. Okay. And we want to know how to write the result in terms of correlation functions on the original Riemann surfaces. Okay, so let's call this sigma 1 and this is sigma 2, right? And here what I'm calling Riemann surface, this basically means Riemann surface with all the punctures built in. Now we can make it a little more familiar. Okay. If we define W1 prime tilde as W1 prime by Q. QW1 prime. So then this equation takes a form W1 tilde prime, no, W1 prime by Q equal to W1 prime by Q, and that becomes 1. Okay, so W1 tilde prime equal to 1, right, in terms of this new coordinate system. Is clear? But for this, we know how to write the result. In fact, we said that this is one way of defining correlation function on the higher genus Riemann surface. So we'll write this then as sum over R. This is on sigma 1, this is on sigma 2. Okay, these dots means whatever else has been inserted on the sigma 1 and whatever else has been inserted on sigma 2. Okay. This is what we had said, that the way to define correlation function on higher genus Riemann surface is by this relation. Pardon? Q is gone because I redefined my W1 tilde prime. Yeah, Q will come back, don't worry. Right? Let's just look at finite Q right now.
W1 and W1. You wanted some coordinate which is BPC conjugate of W1.
Yeah, well, I wanted something that is familiar, right? And earlier, the way I had defined the higher genus Riemann surface is that I said W1 tilde prime equal to 1. And for that, we know what the answer is. Right? That's all I'm using. Exactly.
There's no other way.
Yeah, exactly. Well, there are other ways, right? There are word identities, etc. you can use. But this is the definition of what you mean by higher genus correlation. Exactly.
Insert a complete set of states on the lower genus.
Exactly. Exactly, right? So this is by definition, this is the definition of the correlation. Yeah. So we are going to proceed. So now phi RC will write as phi S. So phi RC is phi S times phi SC phi RC, right? Because this is identity. Okay, I insert this identity in between. So you can write this then as, I'll not write the sum over R because repeated indices is summed over anyway. So this phi R at W1 equal to 0, this sigma 1, this at phi S at W1 tilde prime equal to 0, times phi SC phi RC. Is clear? Yes. The repeated indices will be summed over from now on, right? So both are repeated index. So you are summing over R and S. Now we use the fact that this object, right? Phi s W1 prime equal to 0, W tilde 1 prime equal to 0. This is just the scaling, right? W1 tilde prime and W1 prime are related by scaling. So this I can write as phi s of W1 prime equal to 0 times Q to the HR, Q bar to the H bar R. Okay. HR, H bar R are conformal weights. I wrote it this way, right? Conformal weights of phi s or sorry, HS. Is clear? Now phi SC and phi S have the same conformal weight. Right? Conjugates better have the same conformal weight, right? Otherwise the result will vanish. So this I can write as the original correlation function phi S at W1 equal to 0 on sigma 1. Then original correlation function that phi, how do I write? Phi S, then sorry, first one is phi R, and then phi S at W1 prime equal to 0, sigma 2. Phi SC because L0 eigenvalue is HS, right? Okay, so this is at the level of amplitudes. Okay. But this is at the level of correlation, not at amplitude, level of correlation functions. But we are looking for amplitudes, right? String amplitudes have more than correlation functions. Okay? Because string amplitudes will require that we integrate over Q and Q bar, because those are the extra moduli parameters, right? We of course integrate over all the moduli parameters of sigma 1, all the moduli parameters of sigma 2. But Q and Q bar, if you recall, are the extra moduli that come in. Okay? So you have to integrate over Q and Q bar. Okay? And you have to insert the appropriate B's. Right? The curly B's, right?
Oh,
That B, right? We have to insert those curly B's. Is clear? So now let's look at what those curly B's are. So first of all, there are the usual curly B's associated with sigma 1. Right? Those are not going to change because those transition functions have do not know about Q. Right? Those transition functions only know about the moduli of sigma 1. That is fixed. So they are appropriate. So in the amplitude,
there will be one associated with the circles of W1 and W2.
Yes, indeed. That is coming. Right? Pardon? Yeah, that has to be inserted. But only that transition function knows about Q and Q bar.
Okay, that part of B will know.
Exactly. Right? So all the other B's, right, that you have introduced, right, for the coordinates on sigma 1 and coordinates on sigma 2. See, what are the net moduli coordinates, right? The original coordinates on sigma 1, original coordinates on sigma 2, and the Q bar. Okay? This is the way we classify the modular parameters of the glued surface, right? So the B's are associated with those moduli, right? So the B associated with the moduli on sigma 1, okay, those will only care about the transition functions that are there in defining sigma 1. Okay. The B's that are associated with the moduli of sigma 2, they will know about the transition functions that are used in defining sigma 2. Okay. So here we have the usual product of Bi's for sigma 1. Here we have usual product of Bj's for sigma 2. Okay. And the picture changing operators, which I'm not writing, but they are there. But now there will be an extra set of B and B bar, right, which are the ones for Q. Right? That Q doesn't enter those B's. Right? This is important to remember. Because the transition functions that are used in defining sigma 1 have nothing to do with Q. Right? Sigma 1 didn't even know about Q. Right? Q comes in only when you are trying to join them together. Right? So these B's know nothing about Q, these B's know nothing about Q. Okay? And the transition function, okay, that depends on Q, okay, that knows nothing about the other moduli. Because where is the transition function coming from? It's coming from W1 prime equal to Q. Right? So this has no knowledge of any other transition function. Right? It only depends on, you can see it explicitly, right? It only depends on Q, this part of the transition function.
Here the left is W, right is sigma s tau s.
Yes, exactly.
Something like
Yeah, so W1 and W1 prime will be playing the role of sigma s and tau s. Right? Okay. So the first thing to notice is that the set of B's factored into one associated with sigma 1, one associated with sigma 2, and then two more, right, which are associated with the parameter Q. Is this point clear? Okay. So now let's try to figure out what is the B that comes from parameter Q and Q bar. So you have to insert dq wedge dq bar, bq, bq bar.
reductive, but because B itself had a sum over all cycles.
All cycles, except the other cycles don't depend on Q. Exactly, they'll just trivially vanish.
Cycle will vanish there.
Exactly. That's all I'm saying. Right? That's why there is a separation of which cycle depends on what moduli. Right? So that's exactly what I'm saying, that there is a factorization between the cycles. So now let's look at write this equation sigma s. You could remember sigma s is equal to fs, tau s, and q. In this case, the variable is q. Right? So the integral, so the b q will be integral d sigma s, b sigma s, del fs, del q, plus the other one, right? By other one, you not contribute complex conjugate, and then let me write it, plus integral d sigma s bar, b bar sigma s bar, del fs, del q bar. Okay. So what is fs here? So we have the relation w1 prime, w1, this is our sigma s, is equal to q by w1 prime, right? So this is fs of q. This is fs of w1 prime and q. Okay, this is my tau s. So del fs del q. This has to be done at fixed tau. Okay. So this is 1 over w1 prime. Clear? Del fs del q bar is 0. Del fs del q bar is 0. So this becomes integral dw1 BW1 1 over W1 prime. Okay. But 1 over W1 prime I can replace by W1 by Q. Right? On that circle W1 prime is equal to Q. So this becomes 1 over Q
RS by del Q. In PQ.
Sorry, yes, thank you. Del Fs bar del Q, thank you. So the relation that you are using is del Fs bar del Q is 0. Because Fs bar is Q bar over W1 prime bar, right? So the Q derivative is 0 of Fs bar. The Q and Q bar you are thinking independent, right? So Fs bar is Q bar over W1 prime bar. So this is Q inverse integral BW1 W1 dW1, which you can write as Q inverse B0. And similarly, BQ bar is Q bar inverse B0 bar. Is clear? We will keep this diagram. So then the final expression that we get now this B0 bar, okay, this B0 bar that you are seeing, right? Where does it act, right? You can make it act on this cycle, okay, because you can imagine that W1 and W1 prime can be glued on this cycle, right? Or W1 equal to mod Q to the half. It doesn't really matter, okay, where you put it. Okay. So effectively it acts, you can think of this as acting on phi r, or you can think of this as acting on phi s. Okay. It makes no difference because of this fact that phi r c or phi s c is identity. Okay. A B0 acting here can be moved to the other side. Okay, so B0 bar acting on phi s c is the same as phi s c on B0 bar. Okay, because it's identity operator. Okay. So this means that we can now insert that object here. We can insert that object here. So I'll write as integral dq by q wedge dq bar by q bar, and then phi rc, sorry, phi sc q to the L0 U to the L0 bar, B0 bar, phi RC. Is this clear?
Like the D and the alpha.
Yes.
There you said BQ and
Yes.
then
So BQ bar, where is that integral? Right? Integral is the place where the transition function is taking you from one coordinate to another coordinate. Right? So that you can choose, right? You can decide that after this you will start using W1 prime. Right? In which case the integral will be inserted here. Right? Or you can say that okay, we continue it all the up to W1 equal to minus mod Q to the half, and then at that point you start using W1 prime coordinate, right? Okay. But it doesn't matter because this integral, as long as there is no other pole, right, is the same, the contour integral. Okay. Now I'm saying that, so you can think of this as inserting on this phi s c, B0 bar acting on this phi s. Because here, say you have inserted a phi s. Okay, or here you have, here maybe you have inserted a phi s. Okay. And now I'm saying that you can use the fact that this is identity to move this B0 bar on the other side. Okay, that's what I've done here. Okay. And then B0 commutes with L0. So you can move it anywhere inside this.
Where was that originally?
Pardon?
This BI insertion was somewhere, right?
On the place where you change from W1 to W1 prime coordinates.
That contour integral.
That contour integral, right?
Yeah.
So that place where you change, you can choose either this circle or this circle or anywhere in between.
The coefficient of the Lorentz of B.
Yes.
Not inserted anywhere, it's just some
Integral.
normal of it.
It's a contour integral. Exactly. Yeah. So if
Does
you
not have a location.
no, it's this. It doesn't have a location. It neither does this, right? It's BW, W, DW, right? So this contour integral has to be done somewhere, right? I'm saying you can do it here, right? Yeah. If you do it here, that is the operation B0 acting on whatever operator is inserted here, right?
B0 acting here in the.
Yeah, B0 acting here, right? Or you can insert there, so B0 acting here, right? So let's suppose that you have inserted it here, right? So it would have been B0 bar acting on phi s. Okay. Now you use the fact, so this would have been B0 bar phi s, right? You should have come with. It doesn't matter, even if it's still on the sigma 1 correlator, right? The other side is also a complete set of states. Phi s is also identity, right? Phi s is also identity, so you can move it from anywhere. Okay. So B0 bar phi s c, right? You can rewrite this as phi s c B0 bar. Because this is identity. Yeah, that's all you are using here.
That's how you're placing it in this third.
Exactly. That's how I'm placing it in between the two.
But before this, there was a definition for the amplitude on sigma 1.
Yes.
There, this
Amplitude on sigma 1 has no B0, no BQ. BQ came because we are gluing. There is a new coordinate that has been inserted, right? On sigma 1, it has its own B's, which are associated with all the puncture motion, various handle, the shape of the Riemann surface, and so on. Right? BQ is not part of that. Right? BQ is something new that comes in when you are trying to showing this to objects, right? So from that perspective, BQ is a new object in sigma 1 that you can think of this as an integral around this contour. This is a new operator that we are inserting here.
encircling a lot of things, right? And whole of the sigma 2 in something.
Yes, it is, right? That is on the other side, right? but we don't want to go and deform it to encircle the whole of sigma 2. Okay. We just want to move it through this one complete set of states. Right? So given this in this form, right? Yeah, you can now take this and deform it to make it act on the whole of sigma 2 or deform it to act on the whole of sigma 1. But we'll just choose to keep it in this position. Is this clear?
So it doesn't matter where this B0 are between this sigma 1 correlation function or
Exactly. Yeah, or on the sigma 2 correlation function or here. But you cannot put it here, for example, right? I mean, you have to put it around these functions.
Each B will have.
Yes, exactly. So that will automatically come because when you have the product of the B's, right? You have the choice of you have to choose one of them to be B0, one of them to be BQ, right? So that so that combinatorial factor automatically comes. Right? I'm not going to discuss that in detail, but that all automatically comes. Is this clear? And now you see that it does look like a Feynman diagram. Right? But what is this object? This object is telling us a correlation function on sigma 1. This is some amplitude on sigma 1, right? After you have done the modular integrals on sigma 1. This is some amplitude computed on sigma 1. This side is some amplitude computed on sigma 2. Right? And then you are saying that you are summing over all possible states here, weighted by this object. So this object you can think of as a Feynman propagator that connects the state R to S, phi R to phi S. Right? Because here you have inserted phi R, here you have inserted phi S, right? And then that object is something that is connecting phi R to phi S. So it is in this sense that this way of writing the contribution near the degeneration does look like Feynman diagram. Okay, and we will make it more explicit in a few minutes. Because you want to see the 1 over k square plus m square, right? A Feynman propagator better have 1 over k square plus m square, right? Otherwise, it's not a Feynman propagator, but we will see where that comes from. Oh, anything that to do, right? The 1 over k square plus m square should be there. Numerator may cancel it, right? It can happen, right? Yeah, so numerator will have a factor. Yeah, it can have a k slash plus m. Right?
That also we should see.
We'll see. We can see. Right? But let's first get the 1 over k square plus m square. So we can actually do the Q integral now. Q integral is very trivial. Everything, nothing else, it depends on Q, right? Okay. So you write Q equal to R, and this can rewrite as Q to the HS, Q bar to the HS bar. Okay, because for a given S and R, it's really numbers, right? L0 and L0 bar eigenvalues. So we can change variable Q equal to R e to the I theta, Q bar as R e to the minus I theta. Yeah, mod Q between 0 and 1. The Q is a complex variable, right? So mod Q is restrict between 0 and 1. Unit disk. Basically, mod Q is restrict in unit disk. So this gives you, so dq bar is proportional to R dr d theta. And this matrix element this is proportional to R to the HS plus HS bar e to the I theta HS minus HS bar. Is clear? So we have integral dr d theta r dr d theta. So let me write this from 0 to 1, theta from 0 to 2 pi, e to the power r to the power hs plus hs bar, e to the power I theta hs minus hs bar. And then finally, we have a dq over q, dq bar over q bar. Okay? So times 1 over r square. This is from q bar. Okay? So the net result is that integral 0 to 1 dr r to the power h plus hs plus hs bar minus 1 and integral 0 to 2 pi d theta e to the I theta hs minus hs bar. So the theta integral basically gives 2 pi delta hs bar. Okay? This is telling us that the only states that propagate are the ones that satisfy L0 equal to L0 bar. And this is 1 over hs plus hs bar r to the hs plus hs bar between 0 and 1. Which is 1 over hs plus hs bar for hs plus hs bar positive and it's divergent for hs plus hs bar less than or equal to 0. Is clear? So first of all, okay, let me emphasize that any divergence that you have in string perturbation theory is of this type. Okay. Whenever the string perturbation theory you run into divergent integrals, right, you can identify that origin of the divergence, okay, as due to one of the q's going to 0 and we have a state that is propagating in the intermediate channel for which hs plus hs bar is less than or equal to 0. Is this clear? First, let's look at this case, hs plus hs bar larger than 0. Spectrum is bounded from below, but e to the I k dot x can have arbitrarily negative L0 plus L0 bar, right? So even in superstrings, right, those
These are the ones propagating.
exactly. In the intermediate state, anything can propagate.
That is not bounded.
Yeah, because e to the I k dot x is not bounded from below, right? Okay. If for hs plus hs bar larger than 0, hs plus hs bar has the form of alpha prime k square by 2 plus something. This is the oscillator contribution. But this one is always present. Right? If it carries momentum k, right, just from the momentum you get a contribution. L0 as alpha prime k square by 4, L0 bar as alpha prime k square by 4. Right? So you see that indeed k square has appeared in the denominator, right? This is k square plus something. Up to this normalization factor of 2 over alpha prime, right? That you can absorb either in the vortices, interaction vortices, or in the Feynman propagator. Okay? You have a 1 over k square plus something. Is that clear? This is 1 over k square plus something. Okay? So this tells us that we are indeed on the right track. This is the propagator. Okay? That if you think in terms of Feynman diagrams, right, this is really counting 1 over k square plus something, and that something you interpret as m square.
But we are still covering a part of normalized space because we have integrated Q from 0 to 1.
Yes, but that covers this part of the Feynman diagram. This particular Feynman diagram.
This Feynman diagram.
Exactly.
Which has later property
Exactly.
restored by that part.
Exactly. Right. And it's this part of the diagram that has the 1 over k square plus m square. Clear? People are looking confused or no? Kaustubh is looking very confused. So it is the usual Feynman propagator. That. Pardon? Mass of whatever state is propagating in the middle.
Ordinary POC,
Hmm.
when you have internal propagation,
Yes.
those are optional.
Yes.
But those are still of the same fields, right? What we had in the theory.
There are infinite number of fields here.
Yeah. But not only that, in the internal propagators, you are saying even unphysical things are propagated.
That is always true, even in electrodynamics, right?
What is propagated?
No, the Feynman propagator, right? Eta mu nu over k square, right? A lot of unphysical states propagate there. Longitudinal polarized photons propagate in eta mu nu, right? No, it's not qualitatively different. First of all, only the physical states require k square equal to 0. Clearly, internal photons can have k square not equal to 0. Yeah, but also the polarizations that appear, right, are not necessarily the physical polarizations.
Here, this like this optionalness is that this HS runs over it.
Exactly, HS runs over everything.
So anything in the PFT.
Exactly. Sum over S is over infinite number of states. So all fields propagate. But that is not divergence. Because what happens is the vortex, right? From the interaction vortex here, you get exponential suppression in HS, e to the minus HS kind of terms. And that basically kills any divergence you may have from the growth of the number of states with HS.
States with, there are unphysical states with HS plus HS bar less than equal to 0.
Yeah. So I'm coming to that. How to deal with them. Okay. So this is saying that you are on the right track, right? This indeed has interpretation as a propagator. Okay. Now, for HS plus HS bar less than 0, yes. Yeah. No, GSO odd states will not propagate. Exactly. Yeah. That is by conservation, right? If everything else is GSO even, right? Their amplitude with one single GSO odd state will be 0. Because GSO odd states are not going to propagate.
The identity inserted had GSO even or
it may have, but the phi s on in the amplitude, you can say it has GSO even only, but if it didn't have, right, then this amplitude with everything else GSO even and one GSO odd will be 0.
Imagine a degeneration where one GSO odd operator you put on one GSO.
No, because if you have one GSO odd here, one GSO odd there, right, this part of the amplitude will vanish because here rest. That's true, but it's a product of this times that times the propagator, right? Yeah. But just this part will be 0 because if you have one GSO odd and rest GSO even. No, the external states you always keep as GSO even. Yeah, externals are physical. I mean, you restrict to the Hilbert space, right?
Q independence on these two things is ensuring this, I think.
Q independence of?
This-
Yeah,
Amplitude, basically.
yeah.
That is ensuring, I think.
Exactly. I mean, in fact, it's probably even more basic because it's just a Z2 quantum number, right? A Z2 quantum number, if everything else is Z2 even and one is Z2 odd,
Yeah.
then
Yeah, I guess if they were not good, but we wouldn't have been able to carry out this figure. Maybe. Even that was not possible.
yeah, I mean, I'm just saying that this part of the amplitude will vanish if you have a GSO.
One of these.
Yeah, no, both will vanish. Both will vanish because both have GSO or even states in the external line, one GSO or in the internal line, that will vanish. Okay, so what to do with these, right? HS plus HS bar less than 0. Here, if we use string field theory, string field theory in fact gives 1 over HS plus HS bar. It doesn't come through this, right? In string field theory, 1 over HS plus HS bar is the one that you get first. Whether HS plus HS bar is positive or negative, it's just like it's the analog of 1 over k square plus m square. It's when you try to convert this, when you try to relate this to world sheet amplitude, right? You use some kind of Swinger parameterization. This is the Swinger parameter representation of the string field propagator. And as we had discussed earlier, in the Swinger parameter representation, if 1 over k square plus m square is negative, then you run into trouble, right? And that's a sickness of the Swinger parameter representation, not of the field theory or not of the propagator. So if you think from the string field theory perspective, right, then even for HS plus HS bar less than 0, this is the correct answer. 1 over HS plus HS bar. This in the language that is world sheet language, right? The way one states this is that you define the amplitude by analytic continuation, which means that you define it when HS plus HS bar is positive and then analytically continue to HS plus HS bar negative. And that basically amounts to replacing this integral by this. Okay? You simply ignore the boundary term at r equal to 0. So if you use string field theory, it's automatic. If you use world sheet theory, you say that you define this amplitude by analytic continuation. But in either case, the net effect is to ignore the boundary contribution from r equal to 0 here. You ignore the boundary contribution from r equal to 0.
What is R?
R equal to 0. That is q equal to 0. R equal to 0 is q equal to 0. Yeah, q equal to r e to the I theta, right? So the divergence that is coming from q equal to 0, right? From string field theory perspective is a fake divergence. It's just because you have tried to use the wrong choice of Swinger parameterization. The only real divergences are the ones for which HS plus HS bar is 0. Because if HS plus HS bar is 0, then you cannot do anything, right? Whether you use the world sheet integral or the string field theory, you always get 0.
HS plus HS bar is less than 0.
Hmm.
You said we ignore the q equal to 0 contribution.
The boundary contribution. We basically use once you arrive at this formula, you replace it by this.
It's like we are ignoring all the propagation.
Not all the propagation. You are doing integral from q equal to 0 to 1, right?
Oh, only 0.
Yeah. Well, I'm not saying that you exclude 0. That doesn't make sense, right? This is a way to do the integral. That when you do the integral, you will see that there is a boundary term from q equal to 0. That term you ignore. Right? So you declare that this integral, an integral like this, is given by 1 over HS plus HS bar, right? Just remove this step. That is equivalent to analytic continuation, right? In string field theory, that is exactly, you get this first, right? And then you try to make connection with world sheet theory by writing it this way.
this delta HSHS bar
Hmm.
is also there,
Yeah, that basically says that only the level matched states propagate
even in intermediate.
in the intermediate state. Exactly. Well, that's good. I mean, if it does happen, right? Because you saw that if the states are not level matched, right, then defining their correlation function becomes complicated. Right? So it is good that only level matched states propagate in the intermediate channel.
This is also automatic.
Yeah, these are automatic and string field theory because they are the string off-shell string fields are required to satisfy level matching condition. Yeah, same left, right. Same left, right, L0 and L0 bar, right? The oscillators can be different. Yeah, exactly.
But that is defined so that it matches with.
Yeah, exactly. Yeah. Well, you also need that for getting gauge invariance and other things. That if you didn't have level matching, it would be hard to get gauge invariant version of string field theory.
Level matching is different from on-shell, right?
Yeah, it's different from on-shell. On-shell is L0 plus L0 bar equal to 0. Right? Level matching is L0 minus L0 bar. See, L0 minus L0 bar doesn't depend on momentum, right?
Yeah.
Okay, so for HS plus HS bar equal to 0, right? Those are genuine issues, right? And there you have to use the full power of string field theory to solve those problems. You cannot, do this some simple manipulation, right? Because L0 plus L0, when does that happen, right? When this happens when an intermediate state is forced to carry on-shell momentum, right? So the intermediate propagator is forced to carry on-shell momentum, right? So this happens, for example, when there is a mass renormalization, right? Consider a Feynman diagram like this. Here, if you try to put external states to be on shell, k square plus m square equal to 0, right? Then this is 1 over k square plus m square. So that will diverge, right? So even in normal field theory, it diverges, right? If you naively try to evaluate this amplitude, right? And you know that the way to deal with this is that you have to resum the external states, write it as a self-energy correction, right? And then find a renormalized mass and use that. So once you use the language of string field theory, you can do that, right? But otherwise, within worldsheet theory, you don't have a way to deal with this. Right? So if you have once you have mass renormalization at loop order, you have to use string field theory to deal with this system. In the Riemann surface picture, yeah, if this is a torus, this is like 3 vertices coming. On a torus, say a torus 4-point function, when 3 vertices come together, right, that's this divergence. Right? And there, the internal state is forced to be on shell, right? Because this is on shell, right? For this k square plus m square is 0. And here you have a 1 over k square plus m square. Okay? So it's not, you cannot do analytic continuation because this is 0.
Mark points came together, we said, there's some bubbling procedure where we make another sphere and
No, there also you'll have a problem, right? If you take 2 mark points coming together, you are thinking of this? 2 mark point coming together, right? Yeah. So this is this diagram. This is an internal vortex, right? The torus, and then there is a propagator. This is forced to carry 0 momentum. That's a momentum conservation, right? Okay. And so if I have a 0 momentum massless state which gets a non-zero expectation value on the torus, then again it's divergent. Right? And this again in quantum field theory, what you have to do, this then means that you are developing a tadpole, right? And you have to shift your field to find the right minimum. Right? Otherwise, in the Lagrangian, there is a linear term that has been generated at one loop. So in all such cases, you basically have to use insights from quantum field theory, right? And use the language of string field theory to see if you can solve this.
Like there you said, it corresponds to using the right field. Maybe like field is actually shifted. That's what it means there.
This? Yeah. So here it means that there is a linear term in phi that you have generated at one, right? This This one, this basically means that the mass has been renormalized. External state mass has been renormalized.
Oh, right.
Right? So if you don't take into account that fact, but just try to do naive Feynman diagram calculation, okay, then you will get divergence. This happens in normal quantum field theory also, right?
This we cure by doing some LSZ.
Yes.
That's what you're saying.
Yeah. So you have to do LSZ. Right? You have to do LSZ in string field theory, but that you need string field theory and not world sheet theory.
The qualitative level is just the QFT level.
Exactly. So the H plus H bar equal to 0 divergences, you have to treat basically by using the QFT understanding of this problem. No. Perturbatively, it's completely finite to all orders in perturbation. Right? Because as we discussed, right, that divergences come essentially from these, right? And these you deal, I mean, you understand this, what it means in string field theory, and you deal with them in string field theory.
Can there be
No, there is no UV divergence in string field theory. See, the UV divergence would come when, say, the momentum of these become large, right? I mean, if you have a loop like this, right?
this is world sheet time. In world sheet, we see that there is
In the world sheet, you think of these, you see this as UV divergence, points coming together.
points. Come.
Yeah, this divergence, for example, right? This was when 3 points on the torus come together, right? Because your sphere is getting pinched from the torus, right?
Okay.
But from the space-time perspective, all of these are low energy, IR, right? Some propagator going on shell, some internal propagator going on shell. Okay, now I have to say a few more words and then I'll stop. Okay. So the first thing that once you use this rule, okay, then it becomes clear why those boundary terms that you had worried about, okay, all vanish. Okay. Because all those boundary terms came from some q going to 0. Right? That integral of total derivative, right? We said that it has to vanish, and there may be boundary contribution left over. Boundaries are degenerations. Okay. So let's just take a simple example. That suppose you have integral 0 to 1 del r of r to the alpha dr. Okay. So this we can try to evaluate in two different ways. Okay. One way is to use the standard relation that because it is total derivative, it will be a difference between two boundary terms. Okay. So this will be r to the alpha at r equal to 1 minus r to the alpha at r equal to 0. Okay. And this would be diverging if alpha was negative. Right? Okay, so these are the dangerous kind of terms, right? Because you ignore all these boundary terms. But now let's see what it will become if we use the rules that I have said. Okay. So for this, we just do this directly, right? So this I can write as alpha times integral 0 to 1 r to the alpha minus 1 dr. And according to the rules that this is would be 1 over h plus h bar, this is alpha plays the role of h plus h bar here. So this is alpha over alpha, and that is 1. Right? So what is happening? Is this giving this term r to the alpha at r equal to 1, right? It is effectively ignoring all total derivative boundary contribution from r equal to 0. It's not ad hoc. It's if you in string field theory, it's automatic, right? It looks ad hoc from the world sheet perspective, that you're ignoring boundary terms at q equal to 0. But from string field theory perspective, this is the right answer. Right? 1 over h plus h bar. Or if you think in terms of analytic continuation, right? You define the boundary terms by analytic continuation. Suppose you decide that all integrals will be defined by analytic continuation. You define it where they are well defined and then analytically continue.
sections and everything.
Yes, it makes sense in the Hilbert space because I can always pull it back to the moduli space, no? Because ultimately the integration is what is section, which is parameterized by the moduli space coordinates. Yeah, you can analytically continue or the integrals, right? Except for in this h plus h bar equal to 0 kind of problem is that, where the momentum gets fixed, right? As long as the momentum is variable, right, you can analytically continue in that momentum. Okay. So from the world sheet perspective, you ignore the boundary term by saying that you will work in a region where the integrals are convergent near the boundary. There the boundary terms will vanish, and then you analytically continue the result. From the string field theory perspective, right, the correct result is this one, 1 over alpha, right, because that is a propagator. And then there is a confusion about boundary terms. Confusion was that we had this, we showed that if you have two different sections, right, if you have integral of a total derivative, we set it equal to 0, right? But that can be set equal to 0 only if the boundary terms vanish, right? So what I'm saying now is that why does the boundary terms vanish? Why can we ignore them, right? That as long as you can use analytic continuation, you go to a region in the momentum space where the integrand actually vanishes at the boundary, right? And then the integral of a total derivative, of course, doesn't get any boundary contribution, right? Because it vanishes at the boundary, right? Or you use the string field theory language, right, where you don't have to do analytic continuation. You simply say that this is my rule, right? That this is fake, that this is world sheet gives you this kind of answer. Right? But if you had directly used string field theory propagator, you would have gotten this answer. Right? So the boundary terms, either if you get divergent boundary terms, that basically you attribute to the wrong use of showing a parameter of a propagator. That's the viewpoint you take from the string field theory perspective.
No contribution from R equal to 0. So
Hmm.
no contribution from Q equal to 0, so no contribution.
Exactly, yeah. Right, and all boundaries are some Q equal to 0, right? And you can use the same kind of analysis. Okay, so I think I'll stop here. So next Tuesday, there is no class. Because next Tuesday, Shivam is giving his defense or the synopsis. And then the other class next week, Thursday's class, and the week after will be online. So I'll send out a message on the board.